discussion about some of the formal tools that we will need. So last time we proved that P of x and t, which is the probability density of finding, say, the particle at position x at time t, is nicely described by something like this. Sorry. Okay. And if you do it so, then the total probability is nicely conserved. And we realized that there are very simple reasons for that, and is related to the fact that the Hamiltonian is an admission operator. Okay, using that, we were able to get this very, very easily. We started introducing a little bit of the ideas of what it means, for instance, to act with an operator on a certain state, okay, and then taking the expectation value with psi1, okay, because simply you remember what is the sorry, not actually, let me just state it, the scalar product, okay? This is our scalar product definition, okay? So something like integral for our wave function oriented thing, integral over space of psi1 star of x times the operator O applied to psi2 of x, okay? Now I remind you that the operator O can be simple, like position or a potential, but can also be more complicated. For instance, might involve a derivative. The momentum, for instance, involves a derivative or whatever you want. Okay? So this object here is not a simple function of x, but it's something that acts on psi2. Okay. An alternative way of denoting this object in a Dirac spirit is the following: psi1 O psi2. Okay, so there is an extra bar here, so the operator O acts on this state, and then you take the scalar product with this. Depending on the times I will use both notations. Don't be confused by this extra bar. More about this when we will discuss a more formal aspect of the theory, the idea of changing representation, and so on and so forth. For the time being, let's continue our discussion, and in particular, if this is the probability density for finding the particle somewhere, suppose that I ask you what is the average position, okay? So average x. Let's do it in 1D. Well, you know that when you have a probability density, the averages are calculated in this way. Let's do it in 1D. Integral of x of p of x and t. Are you familiar with this? This is clear to everybody, okay? Given a probability, to calculate the average, you just integrate x times the probability. Good. So this object here, very naturally, in fact, is written in this form, right? Because this is the integral over x of, remember that this is psi star psi, okay? So let me write one psi star here, the x in the middle, and the other psi here. Okay? So I just rewrote this p as psi star psi in this strange way, okay? And then you realize that this is nothing but psi, then the operator x acting on psi, okay? Which you might also write in the Dirac notation with that or without, as you wish, okay? So the average position x is in fact this so-called expectation value, or also in this way bracket, okay, you see, you put the X operator into the state psi and psi. Now, although we will explain the reason later on when we will discuss about measurement, let me just give you a general story. Suppose that I have some operator A, and I ask you what is the average of A. I denote it like this, okay? Say at time t. Then the prescription is the following. Take the state psi of t and do the scalar product of the state with the A applied to the state. Okay? So, or if you want, you can add here the bar. Okay, so you have to bracket A in between psi and psi. Pretty generalization of that. Alright? So, concretely, this is the integral so far of integral in dx psi star of x and t, A acting on psi of x and t. Okay? Now notice A acts on this state here. Right? These chalks are bad. Okay. Which again means that if I'm asking you, for instance, what is the average momentum, here I should put the momentum operator. Okay? So if this was P, then here I would put minus I h bar, the derivative with respect. It's a terrible chalk. The gradient, okay? Good. Second comment. This implies that here I will not have P, because I have psi star times the derivative of psi. Is it clear? So P does not appear. So unlike here, where somehow I rewrote P as a psi star psi, here I wouldn't be able to do the opposite. Rewrite this thing in terms of a P. Is it clear? This is important because P is not a fundamental quantity. So I wouldn't be able to formulate quantum mechanics in terms of P, of this classical expectation value, but rather psi is a fundamental quantity. Okay? So I have to, the fact the Schrödinger equation is an equation for psi, not for P. Good. Now let's show one simple but important property. Suppose that this operator A is Hermitian. Okay? So you remember that when an operator is Hermitian, let me write here A with A. Okay? Then you know that you can make it pass the border at no cost. Okay? You also remember one interesting property of the scalar product, which is the following. Psi 1, psi 2, the star of it is psi 2, psi 1. Right? If you take the star, you just reverse the order in which the two states are written in such a, because you remember that the definition of scalar product involves a star for the left object. So the exchanging the two makes a difference. You need to take a star. Okay? Good. Let's try to show that if A is Hermitian, if A is Hermitian, then this expectation value of A is real. Okay? Any state, for any state. That's very simple. So remember that this object here is this. Okay? So this object is equal to, we have to show that it's real, but it is equal to psi A psi. Okay? But A is emission, so I can bring it here. Equal to A acting on psi on the left, psi. But the scalar products have the property that if you exchange the two, you get a star. So that's equal to psi A psi star. Okay? So you see that you have that this object here is equal to its star. Okay? Very, very simple thing. Emission is the first step, and then you always have this property, so you get the star. So a number equal to a star means that the number is real, right? Very good. This is very, very general, okay? Any emission operator, okay, has so-called expectation value or averages defined in this way that are real. Then I propose you the following fact. Consider as operator A in one dimension, say the momentum, which is minus I h bar, the derivative with respect to x. Okay? And there is a small exercise that lets you appreciate that if I calculate the expectation value of P, which again is psi P psi, or written explicitly in one dimension, is the integral of psi x minus I h bar, the derivative of psi x. Okay? Let me omit the dependence on t, it's not important. So this object is real. We just show it in general because P is emission. And notice here there is a 9. Okay? So it is real in spite of the I, or maybe I should say because of the I. Good. And remember that the idea behind the story, the emission nature of P, is that the integration by parts brings a minus sign when you move the derivative from here to there. And so the I is just what you need to undo that minus sign of integration by parts. Okay? Is it clear? Good. The second thing that I would ask you to explicitly look is that this object here cannot be written in terms of P of x, which is modulo squared of psi of x. Okay? Just to restate the fact that P is not a fundamental quantity, but psi is. Okay? Good. Let's proceed with a few technicalities. In the notes I discussed here about commutators, but we have already discussed commutators for X and P operators. So the fact that in quantum mechanics, in general, when you work with operators on functions, the order in which you operate on those functions is important. You cannot exchange them. And in fact, we already discussed the fact that X and P commutator, X, P commutator, is a very important fundamental quantity, I, H bar. In the notes, I ask you to practice a little bit with commutators. There are a couple of exercises. Okay. For instance, you can prove that if I have A and B, and then I want to calculate the commutator with C, which I remind you means A, B times C minus the opposite, C, A, B. Okay, that's the meaning. Then you can prove, it's a very simple thing, by adding and subtracting things, that this is equal to A. So you see I have two objects. I can distribute it. I can take A out. So A times the commutator of B and C. Or I can distribute by taking B out from the back door. So I have plus A, C, commutator B. Okay? You can prove it very easily, either by just showing that there are cancellation in this term, or adding terms here and trying to reconstruct those two things. Okay? Obviously, a similar story holds if the two operators are here in the second term, so there is also a corresponding formula for this. Okay? Try to see it. And then there is a small exercise that asks you to show a few things, like, for instance,
Professor.
Yeah.
You said the momentum operator is Hermitian.
Yeah.
No, I'm just not convinced about it.
Correct. Which means that this object is exactly equal to P applied to psi. Let's repeat. Let's rewrite what this is. This is integral. Then the momentum applied to psi, and then you take the star. So minus I h bar, the derivative with respect to x of psi, okay? Star, you see? So the star is applied after the application of the p, times p of x, okay? So obviously there is a plus I. Here there is a minus I, okay? The minus sign difference is precisely what the integration by parts commands. Okay, so these two things are the same, just because the I brings a minus sign.
Oh,
is it clear?
So it's not the momentum operator, but the expectation value.
The momentum operator is an operator, and we said it's Hermitian, but the reason why it's Hermitian is that somehow you can bring on, you see, here is when the two states are the same, but you can repeat the same construction when these two states are different, and this shows that P is Hermitian. Okay? So P is Hermitian. To show that P is Hermitian, you have to show this. Psi 1, P psi 2 equal to P psi 1, psi 2 for any psi 1 and psi 2. Okay, so you have to show that this trick of integration by parts correctly works for any states. In particular, if the two
Excuse me, Professor?
Yeah.
Can you please write it a bit large? I cannot be able to write what you have written the Hermitian operator.
You are right. Where should I, for instance, here?
Yeah, that one, please.
Ah, that one, yes. Okay, so.
Thank you.
Sure. This object here, due to the Hermitian nature, is equal to this psi, which is equal to the integral of minus I h bar, the derivative of psi, okay? Then you take the star, and then you multiply by psi of x, okay? So I was just commenting on the fact that these two expressions are exactly the same, and the way you can prove is integration by parts. Okay? So you bring the derivative, say, from here to the other side here, okay? And you get exactly this.
Yeah, thank you.
You're welcome. Okay. No, what I was asking is to practice a little bit more with commutators. For instance, apply this type of rules to calculate the commutator of, say, x and p squared. Not p squared. Okay? So it is this rule that we have to add. X, p. Okay? The rule, by the way, is that, again, distributing, so you can take the c out or the b in front. And you have a, b, c plus b, a, c. Okay? So apply that and calculate this, and you should find something like 2i h bar the momentum. Okay? The fundamental commutator obviously is involved, so you know that x and p is equal to I h bar. And if you use this, you get it. Then you can prove other things. For instance, you can prove that x p to the power n is equal to n I h bar p to the power n minus 1. Okay? Try by mathematical induction. Try. Okay? Good. Which suggests, yeah, you see there is like a derivative rule. You bring down n and you get n minus 1. Excellent. Now, let's discuss another very important mathematical tool. So far, we discussed what it means that A is Hermitian. Now, given an A, I consider what it means a Hermitian conjugate. It is denoted by this dagger. Okay? It means the following. I take two states, psi 1, A, psi 2. Okay? Any two states, psi 1 and psi 2. And I calculate this expectation value. If I can find another operator such that this object is equal to this, okay, this other operator is this object here, then you say that this new operator is the Hermitian conjugate operator. So in words, it is that operator which, acting on the left, reproduces exactly the action of the operator right, A, acting on the right. Okay? Now, so far, we encounter only Hermitian operator. For Hermitian operator, A dagger is equal to A, right? So, Hermitian operator are Hermitian conjugate of each other. Okay? You can bring the A to the left. But in general, that's not the case. Example, closely connected to this. Suppose that A was the derivative with respect to x. Okay? So this object here, I write it explicitly, is integral in dx psi 1 star of x times the derivative of psi 2 of x. Okay? So my question is, what should I write here, integral in dx? What should I write here in order for this to be correct? What operator should I put here? Not the derivative. If I put the derivative, so if I use here derivative with respect to x of psi 1 of x star, I do a mistake. Because integration by parts tells me that if you forget about the values at minus infinity and plus infinity, which is the boundary part, you remember integration by parts, right?
Yeah.
Okay? Those values give you 0 because the functions are normalized, and therefore they have a norm that is finite, therefore they go to 0 plus infinity. But there is a minus sign, so when you bring the derivative from here to there is a minus sign, okay? So the correct object is minus the derivative. In other words, if A is equal to the derivative, then A dagger is equal to minus the derivative. Okay? So you see that it is different. Good. There are a few things that you can prove about emission conjugation.
Sorry?
Yep.
You said that A equal to A plus when the operator...
Dagger, not plus. This is a word, a little word, okay? Dagger. Although sometimes it's also indicated by plus, but I mean, people call it dagger. Yeah.
It's for emission operators, and we say that P is emission,
Yes.
right? So why is the...
There is no I here.
Ah,
You see? I'm missing on purpose the
It's
I.
not P, operator.
No, it's not P. It's just the derivative without the I. And without the H bar, but the H bar is irrelevant. It's a constant. But there is no I. Because of this absence of I, you get the minus. And the operator is not the same. It's not emission conjugate. Okay? A few things that you can prove about emission conjugation. The first is that if I have two operators, A and B, and if I want the emission conjugation of the product of them, that's equal to B dagger, A dagger. Okay? In other words, you have to exchange the two things in the daggers. You probably remember a very similar rule for the transpose of a product of matrices. Do you remember from linear algebra? If I have two matrices, A and B, and I ask you what is the transpose of them, then that's equal to B transpose times A transpose. Okay? It's a very, very similar rule, and in fact, it is born of very similar stories. Okay? Good. This is very easy to show, but well, try. Okay? The second thing is the following. If I want the emission conjugate of the emission conjugate, so I apply the operator of emission conjugation twice, guess what it comes? A. Okay? So it's a self-dual thing. Okay. Good. Other thing. If I have an emission operator and I multiply by I, so suppose that A is equal to A dagger, so A is emission, then I ask you, what is IA? What is the dagger of IA? And the answer, that generically this would be minus I, the dagger of A, but since this is emission, this is equal to minus IA. Okay, so when you have complex imaginary things, you have to be careful. The emission conjugation brings extra minus sign for the very simple rules that in the scalar product, if you remember, there is always a star in the left, okay? So whenever you put eyes there, you change the sign, okay? So try to make sense out of this. It's a very simple thing.
Professor,
Yeah.
is it the anti-Hermitian property?
Yes. It is called also anti-emission, but never mind for the name. Okay? I mean, it's I times an emission operator. Okay, final thing, the emission conjugation is linear. So if I want, for instance, the emission conjugate of the sum of two things, then that's equal to A dagger plus B dagger. Okay? With these things, you can essentially calculate the emission conjugate of any linear combination of two operators. In particular, the linearity is triggered because the scalar product is separately linear, or better yet, linear on the right, anti-linear on the left. But it is separately linear in this broad sense with respect to both sides. Final thing, suppose that I have you A plus IB, A and B are emission, but I consider this funny combination, A plus IB, okay? Then, what is the emission conjugate? Rule is very simple, it is linear, and therefore you do it A dagger, but A is emission, so you just keep it A. And then I have minus I, B dagger, but B dagger is equal to B, so that's the result. Okay? So if I have this object, I just need to change the sign here. All right. Good. So practice a little bit with the emission conjugates to prove these few properties. And now we are ready to discuss Eisenberg uncertainty principle for wave functions in more general terms than we just saw in our second lecture. Okay. Very good. Now, if I have some probability distribution, like this, okay, some P of x, and I ask you, what is the width, the spread of this probability distribution? How you characterize, in the most simple way, the spread of a distribution? You know that there is a concept of variance, right? Standard deviation. You remember how it is calculated?
Expectation of is
The square of the, say, this is x, okay? I have to calculate the square of x minus the average of x squared, okay? Each one of those things is integral in dx x squared q of x, right? And this object is integral in dx x p of x, and then I have to square this thing. Okay? You can prove easily, you probably remember, that this is nothing but the expectation of x minus the average squared. Okay? This is nice, first of all, because it's a bit more compact. You just subtract to x its average, then you square, and then you calculate the new average. So it tells you essentially, if this is essentially the average of x, how much this variable x minus the average spreads around the average. The interesting fact about this way of rewriting is that it is immediately obvious that this is non-negative, right? You might be suspicious, say, the difference of two numbers Can this be negative? No, it cannot be. Yeah, that's very general. All right, is this clear? This is probability in some sense. Okay, but I discussed with you that somehow the same concept applies to operators. So if I ask you what is the average, okay, if I want to know the spread in the measurements of this position, I would call it delta x squared. A very natural thing to do is to calculate the expectation value of x squared, which you remember I do it by putting the psi and the psi here, minus the expectation value of x squared, okay? And precisely as discussed there, this is also equal to the expectation value of x minus its average squared, and then calculated with x. Okay, it's a bit longer to write with all this x psi appearing and all these hats everywhere, but it is the same, very same concept. Okay, so this somehow will tell me about the delta x in the spread of the probability of finding a certain particle around an average value. Okay, good. This is my definition, by the way. I define the spread delta x squared to be precisely given by this average. Now, you can do the very same thing on P. Okay? I can calculate the average momentum, and I can calculate the P squared, and take the spread in P to be precisely given by an expression like this. Let me just skip these two intermediate steps. So it's psi, the momentum, minus the average momentum, squared P, psi. Okay? If I want to save a little bit of chalk, I might rewrite this as later on as average P, okay? Intended to be on psi. If I do not indicate it is on psi. Okay? Good. Now, I want to prove to you the following things. That these two objects obey the following fundamental inequality. That delta x times delta P is greater or equal to h bar over 2. Okay? This is called the Eisenberg uncertainty principle. How we do that? We do it in this way. Is it clear? The statement is clear. Okay? So these two objects are defined by these two things, and I want to prove to you that the product, the square, has to be greater than a certain quantity related to h bar. Good. Let's prove it. First of all, let's consider the following object. So I consider the quantity x minus the average of x, okay, plus I, alpha is some real number, p minus the average of p. Okay, let's look at this object. This is an operator, the operator x minus its average, okay, which is a number. Plus I, notice the I here, alpha is real, some number that I don't know, never mind. And then I have p minus its average. So you see immediately that this object here is what I have in this definition, and this other object here is what I have here in this definition. But squared. Here I go squared. Okay? So This is an operator. I call it O alpha. Alpha is a parameter, is this real object. All right? Very good. Now, let's, based on this, define the following quantity. D of alpha is a function which is given by the integral over x from minus infinity to plus infinity of the modulus square of, the operator O alpha applied to psi, okay, of x, modulus square. Is it clear? I simply do apply the operator to psi, take the modulus square, and I integrate over all space. So you agree with me that this quantity is, first of all, it's real, and it's also non-negative, right? So this object is greater or equal to 0. Correct? Very, very simple. But you remember what is our notation for scalar product. Our notation tells us that this object can also be written as the operator O alpha applied to psi, scalar product with the same operator applied to psi. Do we all agree on that? Remember that in the scalar product I have to take the star of this times the same thing, and I get the modulus square. Is it clear? Good. Now, now I do a little trick, okay? I want to bring this on this side, okay? What do you think I have to put on that side? In order for this operator to migrate on the right hand side, what do you expect that I should use? Should I use O? In other words, I want psi, then I want O alpha psi here, but I want something for this object. O dagger, yes. Because in general, O alpha is not a Hermitian. You see, this is a Hermitian, this is a Hermitian, but here there is a 9. And in fact, we just learn how to calculate those combination of two Hermitian with an I. Okay? You get a minus sign. Okay? But let's indicate by O alpha. O dagger. All right. Shall we calculate this object? Why not? Okay? So here it is. I will be, however, slightly compact. So this is the average of x in my next things, and this is the average of p. Otherwise, it's too much. Okay? So let's calculate O alpha dagger, O alpha, okay? That is equal to x minus the average of x, okay? And then I have the plus I becomes minus I alpha p minus the average of p. Is it clear? This is the left. And then I have the right, which is x minus the average of x, plus I alpha p minus the average of p. Is it clear? Good. This is O alpha and this is O alpha dagger. Shall we do the calculation? This times that is precisely what you have there, okay? I'll write this as x minus average of x squared. Then there is another simple term that is this. This times that is the square of p, okay? Let's see, the factor is alpha square times minus I. So it's plus alpha square p minus the average of p squared. Okay, so these are the two things that appear into delta x and delta p nicely. Let's now see the cross term. So this times that, and this times that. Here you have to be a bit more careful, because you see that I have x times p, and then I have minus p times x. Okay? So you immediately see that this involves a commutator. And by the way, these quantities that are numbers, okay, if you check, they cancel out exactly. So the numerical subtraction that you make doesn't matter in this commutator. The only non-trivial term that survive is, I write it here, plus there is this I alpha, okay, and then I have x p minus p x. Check that that's what you get. Okay? But you know how much is this, right? This is the commutator of x and p, and you know that this is equal to I h bar. Always. Fantastic. So what we have is that this quantity here altogether is just a constant, and is equal to minus h bar times alpha. Good. So let's now evaluate this quantity in between the state psi. Okay, so I put the psi everywhere. Here, 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 here. And what about here? Well, here psi is normalized. The result is still minus.
Professor,
Yeah.
what you just used is not, it's not visible.
What?
It's not visible.
No, what you just written is not visible.
This one. Is that too small?
Just over from there.
From where? From where is not visible?
That you pass last part that you just put where it is negative h bar alpha.
Ah, this?
Yeah.
This is not visible?
Yes, is one.
Okay, let's redo the algebra here. Enlarged. Okay, this is plus I alpha times the commutator of x and p, but the commutator of x and p is equal to I h bar. Okay, so you do the two things, and that's equal to minus alpha times h bar. Is it now better?
Yes, thank you.
Okay, good. Now, sorry for inserting small things around. I write this here again, minus alpha h bar, and I erase this. Okay, good. Our goal is to calculate this, and now we have determined this object here. Okay, it's written here. Sorry, let me eliminate these small things which make confusion. So O is written there. So what about this? This is equal to the expectation value of this object, x minus, average of x squared on psi, okay, from the first term, plus alpha squared p minus the expectation value of p squared of psi, and then I have minus h bar alpha psi psi. Okay? Now, this is 1. The state is normalized. This quantity here is by definition delta x squared. And this quantity here is by definition delta p squared. Okay? So let me rewrite for you the expression for this function d of alpha, which again is greater or equal to 0. I write it here. So let me start from this quantity. Alpha squared delta p squared. Then I write this minus h bar times alpha. And then I write plus delta x squared. Is it clear? So this function is a parabola in alpha. You see, you have quadratic term, linear term, coefficient. And I know that this should be non-negative. Now, do you know how parabolas can avoid being negative? In other words, if I plot this function d of alpha, I should have something like this. Or like this. This is still okay. But certainly this is not okay, because here there is a whole region, so no. Okay? Can you tell me what is the condition that I have to impose on this coefficients here in such a way that I'm not in this condition, so there are no negative terms?
On the P.
Well, no, I don't. The mathematical condition is that this object does not have real solutions, right? A second order equation can have real solution, but I should avoid it. So you remember how to avoid that the second order equation has real solution? I should look at the discriminant, okay? So if I call this object A, this object B, and this object C, you remember that the discriminant, okay, delta is equal to B squared minus 4AC, and in order to be in these two situations, this should be less or equal to 0. Otherwise, I would have solutions to real solutions, right? And the negative part. Is it clear to everybody? Let's write the discriminant now. The discriminant of this quadratic thing is equal to B squared. So h bar squared minus 4. A is equal to delta p squared. And C is equal to delta x squared. Okay? So this discriminant should be less or equal to 0. Let's do one more step. You bring this on this side, and you have that 4 delta x squared delta p squared is greater or equal to h bar squared. Okay? You divide by 4, allow me to do that. Okay? You take the square root of everything, and you deduce that delta x times delta p should be greater or equal to h bar over 2. Okay? Is it clear?
Yes.
Okay? So it's a very, very simple application of essentially ideas of Hermitian operators, in particular combinations of x and p, and then simple ideas of algebra, of second order equation. Notice how crucial it was that here I used alpha here and I put the I there, so that I have this minus thing. I have to construct a proof appropriately, okay? So if I just put a generic quantity here, I wouldn't be able to nicely explore this quantity. So I want some real function of a real variable. All right. Is it clear? A very, very similar proof holds if I want to calculate the spread of two operators A and B. Okay? In other words, from A I can calculate the average of A, the spread in A, which is somehow delta A. Okay? Again, just define it to be the average of A squared minus, say, A minus the average of A squared. Okay? B, same thing. And then I can write a formula on the generalized Eisenberg uncertainty principle, what the delta A and delta B should be equal. And you will see that here you do have something involving the commutator of A and B, okay? Averaged over the psi modulus of that. We will see this later on. So I think that the correct formula is something like psi modulus divided by 2, or something like this. Okay, never mind. We will see later on that uncertainty principle can be written also for other operators, and not only X and P. And the right-hand side of an uncertainty principle always involves a commutator. Okay, so if two operators commute, the product of their spread can be made arbitrarily small, which means that you can find situations where you determine them very, very precisely. If they do not commute, it's never possible to determine them very precisely both together. Okay? So the idea is that either you determine X precisely by squeezing the wave function in X space, but at that point you need very, very, very momenta, and therefore the momentum space wave function is very broad, and vice versa. Remember the wave packet discussion at the beginning. Shall we? Okay. Good. Shall we make a 2 minutes break so that I can breathe? Can you can breathe? Okay. Okay. So just a 2 minutes break, okay?